I have started to put together a little integer mathematics library in order to help us to write some more complex functions. So we're going to start off with the absolute value of a number. So for example, if we were to take the number 5, then the absolute value is the distance between 0 and 5, which is just the number 5. If we take the number minus 5, then it's the distance between the point 0 and minus 5, which is again is a distance 5. So basically it's going to take all of the negative numbers and turn them into positive numbers. So the absolute value of minus 100 is plus 100, and the absolute value of plus 100 is plus 100. So it's quite a simple little function, but I've had to do a little bit of changing of the circuit here in order to get it to work properly. So the first thing to note here is that if we were to head down into the CPU, now again I'm going to create the full video for the actual course, Design a CPU 2, and you'll get the full video of all of the details of this within the course. So this is, if you like, is just a little cameo for the YouTube. So if we head into the ALU, the main change you'll see is that the comparison was originally made here within this exclusive OR. So the exclusive OR actually had a couple of points coming off, and one was for A is larger and one for A is equal to. Now that wasn't going to be any good for us, because if we are going to be dealing with negative numbers, we want to make sure we've got a comparator which will deal with 2's complement. So what we can do here as a quick fix and an easy fix is to leave the exclusive OR as it is, and then just add in a comparator. So you can see here I've picked a comparator from the primitives here within Logisim. Now this isn't a cop out. If we wanted to, we could design and build a 2's complement comparator, but it just goes into a lot more detail than we need for the moment. We really just want to be able to use some of the functionality within Logisim. So we have the comparator here, and we have the greater than and the equals to, and it just comes off, and again it just goes out through the same points. A is larger and A is equal. So, and you can see when I click on it, it's set as 2's complement. So it means that whenever we have, for example, a negative number like say minus 10, well, minus 10 is actually smaller than minus 5, okay? But if we were to put that through the little comparator that we used here, it wouldn't have dealt with negative numbers. It would have said that the number minus 10 is larger than minus 5 because the actual value 10 is a larger value than 5, but it's negative. Okay, so negative, it works the opposite direction. So that's why we've had to put in this 2's complement comparator. Now I've already built into the assembler the functionality for dealing with negative numbers. And again, I will cover that on another video within the course. So that's the first thing to note here. Now another thing to note, if I was to head back up to the top level, I did fix a few of the jump options here. So if I come down into the control section, we had a section here for the jump if, and I've changed a few of the options about. So for example, if I talk through these, that's JALT, that's jump if A is less than, jump if not 0, jump if not carry. We've got a jump if positive, so we can test whether it's a positive number, we've also got a jump if not equal, the jump min, which is jump minus, it tests whether it's a minus number, and I'll show you that test just in a moment. Jump of 0, jump if a is less than or equal to, jump if a is greater than or equal to, jump if equal, jump if a is greater than, and the jump if the carry. There's a few here extra as well I put down as spare. We're not really using them, okay, for the moment. So we've got 3 here that we could potentially add on if we want to, okay. Now, one thing to show you here is the test for the positive or negative. Now this is really quite straightforward. We know in 2's complement it's going to be a negative number if the highest bit here on the 16 bits is a value of 1. Then we know that's a negative number. So all we need to do is just take that 16th bit out and test and see whether we get a 1 or a 0. So if this is a 1, it's a negative. If this point here is a 0, then it's going to be a positive. So we can just take that out, and you can see that when I take it out, I've had to take it out, and we have an extra value here in the flag now. So we've got a carry, a is greater, equal to, we've got the 0, and now we've got n for a negative. When it goes high, it means it's a negative number. So we're going to take these, and these go into the control section, and that value for negative, again, it goes in here as an extra test here. So that's the changes that I've made in the circuit, and now what we're going to do is we're going to go through an example of the an absolute value function which has been generated for this CPU. So I will bring up the code just now. So that's the code here. Hopefully you should be able to see it. Make this any bigger? No. I think you can see that okay. So what we're going to do is we're going to work this as a function. So we're going to take a value which is in memory somewhere, and we're going to return the absolute value. So if it's a negative value, we'll make it positive. But we're going to do that using a subroutine. So what we want to do is we want to save this as a little function in ROM. Now I haven't gone ahead here and saved this in ROM. It's just sitting in the RAM for the moment, but it's easy enough for us to go ahead and take this code and then just change it a little bit and stick it in the ROM, so that whenever we call this subroutine, we'll have a number, and we'll pass that number into the subroutine. It will work out whether it's positive or negative. If it's negative, it will return the positive value, and it will put that back into the memory location. Now, we've seen in previous videos we had several different methods of passing variables into the function. Now, the one that's most prevalent and the one that we're going to be using is passing the value in using the stack. So we're going to put the value from the memory location onto the stack, and then from within the subroutine we're going to pull that value from the stack and put it in a different memory location. In effect, this becomes the local copy of that that value, or the local copy of the variable. And you can mess about with this without messing up the global copy. So here's the little bit of code here, and I'll try and talk through it first of all. So the very first line here is just a kind of setup line. Okay, it's not really part of the code. We're just wanting to put a number somewhere in memory. So I could put any negative number. So I could put in say the number minus, well, I'll put the number -1 for the moment. So we're putting the number -1 into this memory location. So that's just a random number sitting somewhere in memory. Now what we're wanting to do is we're wanting to load this number. In this case here it's -1. We're going to load the value of x into R0. Okay, now the value of x here is a memory location. So we've got a value for x here, which is the memory location 8150. So we're going to load the contents of 8150 into R0. So in effect all we're going to do is we're going to take the -1 and put it into R0. We're then going to push that value R0 onto the stack. Okay, so -1 will then go onto the stack. So I'll change that to -1. Now that -1 is on the stack, we're ready to jump to the subroutine. So I've called the subroutine math_abesx. So we jump to that subroutine. So there's a subroutine here. Now whenever we jump to the subroutine, it automatically puts the return address in the next position within the stack. So what we can do is we can pop that return address off of the stack and put it into register R0. And then we can store that return address from R0 into this memory location here, which is called return address. And you can see here we've set it up here with the DS directive. So we're going to store the return address in this memory location 0x8100. And then we can pop the next value off. So when we pop the next value, that's the actual value -1. So we're going to take -1 off and we're going to pop it on to register R1. And we can make a local storage or copy of this in this value, this position here, which is save_x. So we can take a local copy and we can save it in this memory location here, save_x, which is going to be 0x8101. We can then get through the comparison. So we can compare the value #0 with the contents of register R1. Now, so we're comparing 0 with -1, and we are going to jump if A is less than. Okay, so if the value is less than 0, we know it's a negative number. So we're going to jump to the convert. So if that's the case here, we'll jump to the convert here, and we're going to take the value that we have here, and we're going to put the value FFFF into register R2. So this is us adding on 2 to the power of 16. So we're adding 2 to the power of 16 onto it in order to get the equivalent positive number. So we're going to be subtracting the 2 to the power 16 off of it to get the equivalent positive number. So we put that into R2, we do the subtraction, so we're subtracting off 2 to the power of 16 and we leave the value in register R1. So that will now be the actual number 1 as opposed to the number -1. Now we push that value onto the stack. So we've now got the number 1 on the stack, and we jump to the return address. Okay, so we then jump back up to the return address up here, which is the point just after the call, and we pop that value, which is 1, off, and we put it in register R1. So register R1 will finish up with that value, and then we jump to the end. So it jumps to the end and it ends the code. Now equivalently, if this value here was a positive value, then we don't jump to the convert, we simply push the value back onto the stack. So if the value was 1, we push 1 back onto the stack, and again we return to this, we jump to the return address, which is up here, and we pop that value back off and into register R1. So what we'll do is I'll run through this. So first of all, we'll have to compile it. So if I run through the compiler, that's it compiled here. And if we were to look at the first pass of the compiler, okay, then we'll see the first pass of the compiler here. Okay, now I can load up the machine. I can load up the machine with the values, so I'll go in here and edit, open up the machine code, close window, and we'll run the simulation. Now I'll just run through the whole simulation and it should run through pretty quickly. And if everything works out right, we should get the number 1 here in register R1. So and there you see it's finished and we've got the number 1 in register R1. So in the code here, we've put the value of -1 in and we've found the absolute value of this, which is the value of 1. So we could do, for example, -20. Save this and we will compile it. Once it's compiled, we can stop this simulation and we'll reset everything. And we'll load up the program again. And we'll run this simulation. So the final answer here is going to be 14. So 14 in is in hex, so 14 is actually 20. So we started off with the number -20 and it's returned the number 20 to us. So it does work, and if you try it with the positive numbers, it just returns that positive number. So what we want to do next is we want to take this piece of code and rather than having it run locally within the RAM, we want to take the actual subroutine here and we want to place the subroutine into a memory location in the ROM. And then whenever we jump, we're going to jump from this part of the code here, which is in the RAM, into this part of the code here, which will be saved in the ROM. The ROM will then return the value back up to a register, and then we can put it for the register back into the memory location. And that will be the very first of our little mathematical integer functions that we're going to generate, and we will generate another half dozen or so of these because they're very useful whenever we go to write other code. For example, this absolute value is going to be used in the Breslau's algorithm in order for us to generate lines. So still lots to do, lots of interesting things that I'm working on. If you're interested in this course and you want to get the full videos with all the detailed explanations, then you can click on the link and it will take you through to my website. Now, if you want to buy the course, you can go and buy it. If you don't, there's lots of free videos on my YouTube channel. But I think at the very least, if you can go in and just log in or sign up to my website, then it's free. All you need is a username and password, and it will just give me extra contacts. So that would be great if you could do that. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.